So now we know how DC motors work. You put a voltage across the input terminals and the output shaft spins. And now what we have to do is figure out how to drive a motor using a microcontroller. So here's a particularly bad idea. Say this is a digital output from your microcontroller. And we connect it to a motor to ground. Okay, so this is a bad idea, obviously. The digital output of our microcontroller is going to have only a very low voltage, and more importantly, it's only going to provide a low current. So this problem is low voltage and low current. So for example, if the motor has 1 ohm of resistance and the digital output is trying to swing between 0 and 3.3 volts, then when it's at 3.3 volts, the motor is going to be asking for 3.3 amps. And of course, the digital output will only be capable of milliamps. So this is a bad idea. We don't want to do this. We need some way of amplifying the output from the microcontroller. So here's another idea. Say that the digital output is used to control a switch. Okay, and now all this output is doing is controlling whether the switch is open or closed. And all the voltage and current is coming from another source. So let me call that plus V. This voltage here could be 10, 20, 30 volts, and it can provide high current to drive the motor with the power that the motor demands. So this is a possible solution, and this switch here is typically a MOSFET or a transistor or some kind of mechanical switch. We won't get into the details of what we're using for the switch, but let's look at a little bit about what problems we might have here. Imagine now that the switch has been closed for a long time, so the motor is running at steady state. So we know that the voltage equation for a motor is the voltage across the motor terminals is equal to the torque constant times the angular velocity of the motor plus the current through the motor times the resistance of the coils plus the inductance of the motor times the rate of change of the current. Now let's assume that the motor is spinning slowly and just get rid of this term here. So now say that this switch has been closed for a long time and then we open it up. What's going to happen? Well, we see that there's been a current I flowing through the motor, but when we open the switch, there's no path for that current to take anymore. So what's going to happen is the current has to drop to 0. It has no choice. There's nowhere for it to flow through. So if we take a look at this equation here, that means that the rate of change of the current here is going to be minus infinity. It's going from some positive value to 0 instantaneously. So what that means then is that the voltage here is going to become minus infinity across the motor. So we're going to have a huge voltage change here between the switch and the plus voltage supply. So with that huge voltage across there, what's going to happen is we're going to get a spark or an arc. And this is a bad thing. We don't want that to happen. So what can we do to fix that? We can put a diode here. And this is called a flyback diode. So the current was flowing through the motor. Now if we open the switch, the diode gives the current a path to take. So it can continue to flow through the motor. Remember, the motor, since it has an inductance, inductors don't like their voltages or the current to change instantaneously across it. So the motor inductor is going to try to keep this current flowing, and the diode is going to give a path for that current to flow. Now when the switch was closed, the diode is as if it's not there because the diode blocks current going against it. But when the switch is open, it now gives a path for the motor to send its current through. So if we imagine that so let's look at the two rules that have to be enforced once the switch is open. So one is that the inductor requires the current to continue to flow. And the second thing is that the diode is going to enforce the voltage across it. Okay. So for instance, if we said that the diode voltage here, the drop from here to here is 0.7 volts, then that means at this location now, when the switch is open after it had been running for a while, this voltage will be minus 0.7 volts, so lower than ground. Okay. So if we write now this equation for the motor, we've got Vm is equal to minus 0.7 volts. So that's coming from the diode. And that's equal to IR plus L di dt. Okay, so right after we open the switch, the current will not have changed instantaneously. So we know that then minus 0.7 volts minus IR over the inductance is now the rate of change of the current. So we can calculate how the current through the motor is changing, and it's going to be some negative value. So for instance, if we had 10 volts, IR was equal to 10 volts initially, then we'd have minus 10.7 volts divided by the inductance is the rate of change of current. And so if we plotted the current, it was at steady state at some current value, then we opened the switch, and now it's going to start dropping by a first order exponential, and the initial slope of that drop is going to be determined by this equation.